Let's imagine for a second that you're lost in the middle of the Antarctic Ocean. The water around you is hovering just barely above freezing, and the surface is capped by hundreds of feet of solid ice. Seeking some sense of direction, you make the crucial mistake of looking straight down into the abyssal water below. Naturally, you might expect to see the usual suspects, perhaps a school of tiny cold-adapted fish, or maybe a cloud of microscopic plankton drifting in the currents. But what you actually find lurking in the darkness is something far more terrifying. Spiders with leg spans wider than a golden retriever are crawling across the ocean floor. Jellyfish with stinging tentacles stretching longer than a blue whale are drifting silently through the currents. And even the most basic, normal-looking fish are somehow abnormally gigantic. And yes, these creatures are all completely real. This isn't science fiction, and it's not a fantasy. In the freezing depths of our planet's polar oceans, evolutionary biology has completely thrown out the rulebook. Welcome to the mysterious slow-motion world of polar gigantism. Polar gigantism is an evolutionary phenomenon that most people have never heard of, largely because it unfolds in the most hostile, inaccessible environments on Earth. At first glance, it doesn't make any logical sense. In an environment where temperatures are consistently below freezing, solar energy is absent for months at a time, and food is incredibly scarce, you would assume that animals would get smaller over time. Basic biology dictates that smaller bodies require less energy to maintain, making dwarfism the ultimate survival strategy for conserving resources. But in the polar seas, the exact opposite happens. In these frozen waters, evolution has supersized the residents, turning small creatures into giants and already large creatures into absolute leviathans. But why? To understand this bizarre paradox, we have to look at the ultimate poster child of polar gigantism, the colossal squid. When most people think of giant squids, they immediately think of deep-sea gigantism, the idea that creatures living in the extreme depths of the ocean grow massive to survive high pressure. But the colossal squid, Mesoneotothes hamiltoni, is actually a product of a completely different evolutionary force. Colossal squids are found almost exclusively in the freezing waters surrounding Antarctica. They spend their entire lives swimming in temperatures that sit right at or even slightly below 0 degrees Celsius. Because of the high salt content, this water doesn't actually freeze solid, but it remains incredibly cold. And in order to survive here, this animal had to undergo a radical physical transformation. Biologically, the colossal squid is a member of the glass squid family. Most glass squids are small, fragile, and almost entirely see-through to hide from predators in sunlit waters. But in the pitch-black, freezing Antarctic depths, transparency is no longer an effective defense mechanism. So the colossal squid traded its transparency for thick, muscular, heavily insulated flesh. To maintain stealth in a world lit only by bioluminescence, it developed a deep, dark red skin. Red light is the first wavelength to be absorbed by water, making the colossal squid practically invisible to its prey. But none of these adaptations explain the sheer scale of this creature. It can weigh up to 1,100 pounds, nearly double the weight of the famous giant squid. What is the secret fuel behind this extreme growth? The answer isn't actually found in the food these animals eat, but rather in the very chemistry of the water they breathe. It is a fundamental law of physics that cold water holds significantly more dissolved gas than warm water. In the freezing polar oceans, the water is practically saturated with oxygen. For almost all marine invertebrates, body size is strictly limited by how much oxygen their cells can absorb. As an animal grows larger, its volume increases much faster than its surface area. In warm tropical waters, there simply isn't enough dissolved oxygen to support a massive multi-ton invertebrate body. Their cells would literally suffocate. But in the freezing Antarctic, the ocean is an endless high-pressure oxygen bar. Because oxygen is practically unlimited, the physical barrier that keeps invertebrates small is completely shattered. Over millions of years, this abundant oxygen has acted as an open invitation for evolution to build bigger, heavier, and more complex bodies. To prove this isn't just a theory unique to squids, we can look at an entirely different class of animals, the Pycnogonidae, or sea spiders. In warm tropical coral reefs, sea spiders are incredibly small. They are delicate, hard to spot, and typically measure just 1 to 2 centimeters across, about the size of a common house spider. But if you dive into the Antarctic Ocean, you will find the exact same family of animals looking like this. These giant polar sea spiders can reach leg spans of over 2 feet. What makes this size increase even more incredible is how spiders breathe. Sea spiders don't have lungs or gills. Instead, they rely entirely on direct diffusion, absorbing oxygen straight through pores in their outer shells. Because they breathe through their legs, having longer, thicker legs dramatically increases their respiratory capacity.
In the oxygen-rich polar water, these spiders have developed giant legs to act as massive, highly efficient lungs, and their massive size has turned them into highly efficient predators. They crawl over the seafloor on their giant stilts, stepping right over obstacles to hunt down slow-moving prey like sponges, anemones, and starfish. Once they find a victim, they use their straw-like mouthparts to pierce the prey and literally suck out its internal fluids like a biological milkshake. In warm waters, starfish are the picture of simple, five-fold symmetry. They are slow, peaceful, and easily recognizable. But in the Antarctic, even the starfish have evolved into multi-armed monstrosities. This is the Antarctic sunstar. Instead of the typical 5 arms, this polar giant can grow over 50 individual arms, stretching up to 3 feet across. And they aren't peaceful herbivores. They are aggressive, highly active predators that crawl rapidly across the seafloor, using their dozens of arms like a giant net to snag small fish, krill, and even other starfish. But perhaps the most dramatic display of polar gigantism is found in the open water column. The lion's mane jellyfish is a species that thrives in the cold subpolar waters of the Arctic and Antarctic. While its warm water relatives remain relatively small, the cold water lion's mane grows tentacles that can reach an astonishing 120 feet in length. That makes it physically longer than the largest blue whale ever recorded. Now, at this point, you might be asking yourself, if the cold polar environment makes things so big, does this explain why polar bears and emperor penguins are so much larger than their tropical relatives? Surprisingly, the answer is no. Polar gigantism is a rule that applies almost exclusively to cold-blooded invertebrates and fish. For warm-blooded animals, a completely different evolutionary law is at play: Bergmann's rule. Bergmann's rule states that within a mammalian or avian family, larger species are found in colder environments, because larger bodies have a smaller surface area to volume ratio. This means they lose heat much slower, helping them survive the freezing air. But unlike invertebrates, warm-blooded animals have to burn massive amounts of calories to generate their own body heat. In the polar regions, food is highly seasonal and scarce. A giant mammal has to constantly forage just to keep its internal furnace running. If a polar bear grew to the size of an elephant, it would simply starve to death. But cold-blooded creatures don't generate their own heat. Their body temperature matches the freezing water, which slows their metabolism down to an absolute crawl. They require almost no energy to survive, allowing them to allocate every spare calorie to slow, continuous growth. This combination of freezing temperatures, slow metabolism, and unlimited oxygen has turned the polar oceans into a highly stable, slow-motion wonderland. In this frozen world, chemical reactions run in slow motion, and generations of animals can take decades to mature. Starfish that would live for 5 years in warm waters can easily survive for over 40 years under the polar ice. But this extreme stability is also the polar giant's greatest weakness. Because these creatures have spent millions of years adapting to an environment that never changes, they are incredibly fragile. And right now, their world is changing faster than ever before. As global ocean temperatures rise, 2 devastating things happen simultaneously. First, warmer water holds significantly less dissolved oxygen. Second, the rising temperature speeds up the metabolism of cold-blooded animals, forcing them to require more oxygen just to stay alive. The giant invertebrates of the Antarctic are suddenly caught in a deadly biological trap. Their bodies need more oxygen, but their ocean has less to give. Recent studies have already shown that the maximum size of polar sea spiders is beginning to shrink in areas where the water is warming. If this trend continues, the giants of the deep may not survive the century. They are living relics of an ancient frozen world, monsters of the deep that deserve our protection before they slip away into the shadows of history. Thanks for watching. If you want to learn more about the strange secrets of our oceans, click on the video on your screen right now. And as always, stay curious.